Okay, in this video, we're going to talk about relative velocity with our burrito drone example. So in this example, we've got our drone. It's moving at a velocity, a steady speed of 3 meters per second to the right. We've got our person here who's going to catch our burrito. The altitude of the drone is 5 meters. The altitude of the person's hand is 1 meter, okay? And the burrito drops and undergoes this parabolic path from the drone to the person's waiting hands. And its initial velocity is 3 meters per second pointed to the right. And in class, we found that the time to fall is 0.9 seconds. And we found that the distance, call this delta x, where the drone drops the burrito is 3 meters, okay? And so now we want to find the velocity of the drone with respect to the ground, the velocity of the customer with respect to the ground, the velocity of the burrito with respect to the ground, and then all of these with respect to the drone. At the moment that the burrito reaches the customer. So at the moment the burrito's here, reaching the customer, we want to find all of these velocities, okay? And so we're going to actually calculate this. So in class, I just gave you the answer. We'll actually calculate it this time. But let's kind of look at what we expect it to be from the cartoon we've drawn. So we expect it to be some velocity, pointed kind of down and to the right, right? All right. Draw that. Something like that. So V final, we expect to have a direction kind of pointed down and to the right like this, okay? All right, so a couple of these we should be able to kind of write down without doing any calculations because they don't change. So the first is that the drone is the drone. So let's think about, let's see, I'll draw the later time in orange. So we've got the drone here, or the burrito here. The drone is now here. It's still moving straight to the right at a velocity of 3 meters per second. And this is in the ground frame, right? So that velocity is 3 meters per second I hat. Okay. And let's also formally define our coordinate system. So we decided in class to draw a coordinate system in the ground frame that started where the origin was here at 0, 0. Okay, so the origin is there, and this is not the way I noticed when I did this problem in class. I moved the coordinate system from what we had used earlier, but let's do it this time. Define that same coordinate system, and then we'll have a drone coordinate system that is right here initially and moves with the drone. Okay, so we'll call this drone. And we'll call this one ground, okay? And then the customer is not moving with respect to the ground. So this is our other easy one. We can just write 0 for the velocity of the customer. All right. And then now let's think about how to write these other ones. So first, the velocity of the drone with respect to the drone is just 0, right? That one's easy. And then the other ones are going to be a little bit more complicated to find. So first, let's think about the velocity of the burrito with respect to the ground. Now, this one is not really a relative velocity problem, but because we skipped it in class, I'm going to go ahead and go through it. So to find the velocity of the burrito with respect to the ground, we want to use both of our velocity kinematics equations. So Vx is just constant, right? So that's the same as v naught x, which is 3 meters per second. And then our y velocity equation is vy naught plus at. And acceleration in this case is negative g. And vy naught is 0. So it's 0 minus g times t. Our t is 0.9 seconds. So we've got negative 9.8 meters per second squared times our time, which is 0.9 seconds. So that's going to give us 9 meters per second. Negative. Directed downwards. Okay. So we can write this now as a vector, which is 3 meters per second I hat minus 9 meters per second j hat. Okay. All right. And now notice that we could also write this as a magnitude and a direction, right? So let's draw that vector. So it indeed points, in some direction approximately like this, which is what we expected. If I draw this velocity vector, it's got magnitude of 3, negative 9. I didn't draw this very much to scale. It should be pointed more downward than it is, but that's okay. So let's say we'd like to find this angle. So the magnitude is going to be, let's just call that the magnitude of the velocity of the burrito, is the square root of 3 squared plus 9 squared, which gives us 10 meters per second. We just have one significant figure here. And then that angle is going to be the inverse tangent of 9 over 3. I'm not using negative 9 here because I'm going to give that angle with respect to the origin and say that it's clockwise. So I want to just consider the triangle instead of thinking about the direction of the angle of that triangle. So that is an angle of 72 degrees below the horizontal. Okay. So either way of describing this velocity would be fine. We could say that the velocity is this given by this vector, or that it has a magnitude of 10 at an angle of 72 degrees below the horizontal. Either one would be fine. Okay. All right. So now we're at a point where we can do the relative velocity, and we want to remember our relative velocity equation. So let's scroll back up to that. Remember that we found that the velocity in B was the velocity in A minus the velocity of the coordinate system B in frame A. I'm going to write that down again right here. So the velocity in B is the velocity in frame A minus the velocity of coordinate frame B relative to A. So what do each of these mean here? So B, we're going to consider to be our drone frame. A is going to be our ground frame, right? So the velocity in our O, our object, is, start with the burrito, but we can do this for each object. So the velocity of the burrito in the drone frame is the velocity of the burrito in the ground frame minus the velocity of the drone in the ground frame. Okay, So we've found each of those up here, right? The velocity, I can't quite fit them all in one thing. Let's just scroll down. Okay, so the velocity of the drone in the ground frame is this one. And the velocity of the burrito in the ground frame is this one, right? So these are all vector equations. So the velocity of the burrito in the drone frame is 3 meters per second I hat minus 9 meters per second j hat, and then minus 3 meters per second I hat. So these cancel out, and we have a final velocity of the burrito in the drone frame of negative 9 meters per second j hat. And this is what we expect, right? Because the burrito, relative to the drone, looks like it's just falling straight down, which is what we find, right? Okay. All right, so let's fill that one in up here. This is negative 9 meters per second j hat. All right. And then the last one we want to think about is the velocity of the customer in the drone frame. Okay, so we're going to use the same thing we did before, plug in to this equation. Now our object is going to be the customer instead of the burrito. So we've got the velocity of the customer in the drone frame is the velocity of the customer in the ground frame minus the velocity of the drone in the ground frame. So in the ground frame, the customer isn't moving, so that first one's just 0. And then this is the same as before, so 3 meters per second I hat. Okay. And so in the drone frame, the customer looks like they are moving backwards or to the left at the speed of 3 meters per second. Okay. Notice that because we used this velocity equation here, we didn't actually have to define a vector that went from the ground frame to the drone frame. Okay, we didn't have to ever write our BA, which in this case would be our drone ground. Okay. So to just find velocities, if you know the velocity in one frame versus the other, you don't have to actually write the R vector. However, let's go ahead and write it because it's good practice. Okay. Now, I don't think I have any room to draw that vector up on my sketch very easily, so I'm going to redraw my sketch down here. So I've got the drone and its coordinate system. I've got my person and their coordinate system, right? And now I want to draw a vector that goes from the origin of my ground frame to the origin of my drone frame. Okay. So in the y-axis, this is not moving. It's not a function of time, right? It's just a steady height. So the j hat component, let's read R, drone, ground, is some I hat component that we'll find in a second, plus the j hat component, which is just 4 meters, right? And now we would like to write some equation for I hat, because we know that it's going to be a function of time, right? And so at t equals 0, the I hat component of R, which we'll call R drone ground X, is going to be negative 3 meters, right? That's what we found above. And then it's going to move at a velocity of 3 meters per second. Okay. And so we can write an expression for this, which is, as a function of time, which is 3 meters per second minus 3 meters plus 3 meters per second times time is the I hat component. And then the j hat component we already found above. So this is the vector of the drone with respect to the ground as a function of time. And then we could also find its velocity by taking the time derivative of this, right? So we've got something that doesn't depend on time, something that doesn't depend on time, so those go away. And then this term is our time-dependent term, and the derivative of something times time is just that thing. So we've got 3 meters per second. I hat is our velocity of our drone on the ground, which is the same thing we found before. Okie doke. And please feel free to send me a message on Slack if anything in these videos is not clear. Cheers. Thanks.